Hello guys, this is a video for Unit 7 Biomechanics in Sport and Exercise Science, and this video specifically is for 7.2 looking at forces, and the topic covered in this is B6 lift and the Bernoulli principle or Bernoulli effect. So in order to understand these things, fundamentally there's two aspects you need to just recall, remind yourself, and one is that things generally move from high to low pressures. Okay, so we may have learnt about that in anatomy. Air pressure inside, outside the lungs is high to low or low to high, high to low, whichever direction it is. Similarly, another thing you need to appreciate is that Newton's third law is the law of action and reaction. For every action, there's an equal and opposite reaction force. And those two principles underpin Bernoulli effect and how we generate this extra lift force. So let's just first of all look at what lift is. Lift is a force. It's an upward force that affects projectiles, objects moving through the air. And in some specific sports situations, we try to generate lift to keep an object in the air for longer, perhaps in order to travel further. Obviously, the example here is a plane, and there are some events which involve flying planes and racing planes, of course. There may be some other more sport-specific examples, but this nicely shows you've got the weight of the object, in this case a plane and a person, gravity acting down through its mass trying to push it downwards. The opposite force is lift. So a typical way to explain this principle of lift, or this force of lift, is through the example of a wing of an aeroplane. Now the first thing to note is the shape of the wing is what we would describe as aerofoil. So rounded at one end, flat on the bottom, and typically a bit sort of downward sloping on the top. Now you might recognize that if you've been on a plane. This video will just give you a little bit of insight to the two explanations of how, when we have aerofoil shapes and airflow moving around that aerofoil shape, we can generate this upward lift force.
So firstly, we'll need a wing. This shape here represents the cross-section of an aircraft wing, also called an aerofoil. This view is if you were looking at it from side on, i.e. from the wingtip looking towards the plane. So one of the most common but incorrect theories which is taught is something called the longer path or equal transit theory, which is based on the Bernoulli principle. So the explanation that this theory gives is that the airflow, the air which is hitting the wing, splits as it hits the front of the wing. The air passes over and under the wing and rejoins at the back of the wing at the same time. So for this to happen, the air flowing over the top of the wing has a further distance to cover over the curved surface. Therefore, it speeds up. As the air speeds up, it causes an area of low air pressure above the wing. The air which passes underneath the wing slows down because it has a shorter distance to travel, and this causes high air pressure below the wing. The end result, this theory states, is that it's this pressure difference above and below the wing which causes the wing to move upwards, and this upwards force is more commonly called lift.
So just to pause that video there, we've got essentially the first explanation of how lift occurs. This is actually what your spec refers to. It is the Bernoulli effect. And the explanation there is that air flows around the top and beneath the object because, and it has to meet at the end here, because beneath the object it's a flat, quick, short route, the air needn't travel as fast, so velocity of the air is reduced. And as a result of that, the air particles get more sort of bunched up together, a bit like in a traffic jam on a motorway. And because they're bunched up and banging into each other, the pressure is relatively high. Now, the airflow that has to go over the top and all the way around and eventually get down here has to travel more quickly around the top. So velocity airflow is high around the top. And because it's faster airflow, the particles are more spread out. A bit like when you've been in a traffic jam and then the traffic starts to move, the cars suddenly start pulling away and spread out. And because they're more spread out, the air pressure is lower. But hopefully what you can recognize is we've generated a high pressure below and a lower pressure above the wing, and this air pressure instigates this upward force of lift high to low pressure. Now, this is one explanation. This is the principle of the Bernoulli effect, okay, the Bernoulli principle. This is what your spec wants you to understand and how we generate lift force in objects. It won't just be aeroplane wings, of course. So the chap in the video will now go on to explain the second explanation. He says it's the correct explanation, that Bernoulli is not really wholly true. Aspects of it are true. So I'll play the video again and he will explain the second, in his terms, correct explanation of how lift occurs.
So the correct answer is that lift is created because a wing or an aerofoil is turning the airflow and directing it downwards. It's not a pressure difference which creates lift. So here comes my attempt at explaining it, and again, physicists, please be gentle with me. So the airflow hits the front of the wing and splits, the same as before. Also, Bernoulli was correct when he talked about the difference in air pressure above and below the wing. And he was also correct in saying that the air which flows over the top of the wing speeds up. Now, the air which passes over the wing kind of sticks to the top of the wing and follows the curve of the upper surface. This sticking phenomenon is known as the Coanda effect. As the airflow leaves the wing at the back, it leaves a slight downward angle because of that curve. That downward deflection also affects the air which passes under the wing and also turns it in a downward direction. It's this turning of the airflow which causes lift. You can generate more lift in two ways. The first is by increasing the speed at which the air passes around the wing. This is generally attained by simply flying faster. You can also increase something called the angle of attack. This is the angle of the wing relative to the airflow. So in this example, you can see that the wing is pretty much pointed directly into the airflow. However, if we increase the angle of attack, you can see that the wing is tilted backwards. This creates more lift because the airflow is turned downwards at a sharper angle. Now, there is a danger to increasing the angle of attack. If you increase that angle too much, there will come a point where the airflow cannot turn and follow the top of the wing. When this happens, the airflow will separate from the top of the wing. This is what happens when an aircraft stalls. There is no steady flow of air over the wing, therefore the wing stops producing lift and the plane begins to literally fall out of the sky.
So I hope you grasped from that second explanation that whilst Bernoulli had some, in his terms, correct facts, it's actually Newton's third law that generates lift. The airflow, combination of the over-the-top airflow and the airflow beneath, making contact with it and being directed down too. We've got this downward air force, which means there must be an equal and opposite upward air force, and that's what he would describe as the cause of this lift, upward force. So we've got Bernoulli effect and Newton's third laws, both ways of explaining how lift is generated. So from the video then, here are some key bits of information to explain Bernoulli and what lift is. Lift is this additional upward force which gives any object, not just a plane wing, could be a discus, could be a frisbee, additional air time, which can mean that it will fly further. And this typically is of aerofoil shape objects, not spherical objects, not round objects. So it needs to have to some degree this sort of shape. Bernoulli suggests that it's this pressure differential, the air velocity creating different air pressures above and below, which causes lift. Newton's law might also be an additional explanation to this. The amount of lift could be increased by changing the angle of attack, so angling this aerofoil more, but also by increasing either the object's velocity travelling through the air, or of course airflow, air velocity. If it's a windier day and the air is approaching the object more quickly, you'd undoubtedly similarly get more lift as well. So I'm not going to read this slide. It is a written version of an explanation of this. Take your time, work through it methodically. That explains lift or the Bernoulli principle. Similarly so, this is to some degree an explanation of the Newton's third law explanation, whereby we generate an angle of attack, we reroute the air because it sticks to the top surface of this aerofoil shape, and that was called the Coanda effect, C-O-A-N-D-A, the Coanda effect. It's directed downwards, so is the airflow underneath. We've got this downward air force, therefore we've got this reactionary upward air force, and that is lift. Be mindful that certain objects have an optimal angle of attack. So too much, as the video explained, and the object, it could be a discus, it could be a frisbee, will stall, will not fly through the air. Too little and there won't be any lift. Again, just simple diagrams to show a discus that's traveling left to right, having an angle of attack and airflow being directed down around it. An aeroplane wing coming right to left, the downward directed force and the upward force. Just an additional bit of information. So frisbees, discus, this applies to these. When we throw these, when we project these into the air, typically they are spinning to some degree. And that's relevant because an object that is spinning is more likely to remain stable in the air, i.e. level at the angle you send it away in. If you throw a frisbee, for example, and don't make it spin, it will flounder, it will wobble in the air, it will be affected by the other airflows sort of hitting it. Whereas if it's spinning, it is much less likely to be affected by the airflow it's going into and will remain in its sort of appropriate position or angle. The other thing, so spinning matters, but also if an object that is spinning has a larger mass, it's also less likely to be affected and become unstable. So the discus here, having a higher mass and spinning, will be relatively stable compared to a discus. So just to summarize, factors that affect lift: the size or mass of the object, the shape of the object, which should really be aerofoil, flat on the bottom, curved on the top, the angle of attack that the object is at. Adding angle of attack increases the downward airflow. The velocity of either the object traveling through the air or the airflow going past the object, and of course particularly stability relates to is the object spinning or not, and its stability will obviously give it additional air time, which in some events and sports is really important. So we've looked at what upward lift is, and I've put upward purposely. The Bernoulli principle is about pressure differentials that cause a high to low and an upward lift force. Additionally, we can explain the lift force by Newton's third law, air being directed down and airflow, the opposing reaction airflow pushing us up. Let's get some sports examples though. So ski jumping. The jumper actually going down the chute before they take off, the ramp before they take off, will assume as tight tucked position as possible. They want to reduce air resistance. They want to increase velocity as much as possible so that when they take off, they're traveling as fast as possible. However, once they go into the air, they assume this position, so they're almost lying what appears to be flat on their skis, but their skis are in a V shape. You can't see it brilliantly in this image, but they are. You can see it a bit better in this image, in this wind tunnel. So this wind tunnel might be a way they may have done some experimentation with this. And the reason they do this is because in the air, they can gain 30% more lift by assuming that position. Now, some time ago, they used to jump with their skis neatly forward beneath their body. Now, when they changed to this technique, they gained 30% more lift in doing so. And the reason is because they're sort of forming a shield. The two blades and the jumper's body form a shield so that when they are traveling through the air, this diagram is showing it right to left, of course, the wind hits them and their skis and is projecting the air downwards, which we know a downwards air force is going to have an upwards reaction force. And similarly so the pressure, we get this high, same reasons it works for our plane wing. We get this high velocity below them, and a lower velocity above them. So they gain more lift by trying to create an aerofoil shape, a short route and a longer route, a force downwards and a reaction upward force. Frisbee's a nice easy example. We have a little bit of angle of attack when we throw frisbees often. We've got the airflow below, short route. We've got the longer airflow, higher velocity, so we've got high to low pressure. And the frisbee will gain some lift as a result of that. And there are various diagrams to do that. We've obviously, with the frisbee, got the spin function as well. If you don't spin your frisbee, it will flounder in the flight, it will stall. Whereas if you have a spinning frisbee, it doesn't. It maintains that sort of position that you want it to. This diagram down here shows obviously different angles of attack. If your angle of attack is too high, let's say bigger than this one, the frisbee goes up and down, very short. If you angle it sort of a lowish, not flat, zero, but a lowish angle of attack, then it will travel further and get because of the lift it's gained. Discus, obviously exactly the same explanation as we've given already. And you can pause the video and have a look at the different diagrams in this one. It's stuff that I've talked about already. The discus is being thrown right to left. This is the optimal angle of release or angle of attack, because this discus gets lift and will stay in the air. This one's too flat, too much angle. This one's a negative angle, it's pointing down, which obviously is counterintuitive anyway and wouldn't get any lift. Upward lift anyway, it would be sent downwards. And these diagrams over here really just talk about the angle of release, so the angle of attack, and also the angle you release the discus at. Just be mindful that this does not apply to spherical objects like the shot put. There is obviously no short flat route, or this is not an aerofoil shape, it's a circular shape, so it does not apply to these kinds of shapes, and that's worth noting as well. So a quick summary slide for you, just the key factors that contribute to upward lift force, and a lot of sports examples as we've gone through already. However, the exact same principle of generating this additional force can be applied in the opposite direction. So as much as lift is generally described as an upward force, if we apply this aerofoil shape the other way around, like this plane over here, the same things works though. It's exactly the same physics, if you like, working on the shape. So obviously a plane wouldn't necessarily wish to do that, but by design, some things that we do and some bits of equipment, and in this case an F1 car, does have aspects of its technical design and structure that are trying to generate a downward force. And the aerofoil shape of their spoiler at the rear here, which again isn't seen brilliant on this car, but there are other images, does that. So air flows over in exactly the same way it would. We've got this short route on the top, we've got this long route on the bottom, we create an upward air force and we get a downward reaction force. Or the short route has a high pressure, low velocity, high pressure. The long route has a high velocity, low pressure. We've got a high to a low air pressure and there's a force heading downward. So it's exactly the same Bernoulli effect, but rather than being directed upwards, it's being directed downwards. All we've done is change the direction and the angle of the aerofoil shape. So if you imagine this diagram on the right was the spoiler at the back of an F1 car, this pretty much shows what I've been saying. Low velocity, high pressure, high velocity, low pressure, high to low, the air is forced down. Now, why is that useful for F1 cars? Well, they very much want to grip to the road, the road, the course, the track when they're traveling at incredibly high speeds. And this is one way of pushing them down towards the ground. So here are a few diagrams. Again, you can pause the video and have a little look at it. It talks you through how this atmospheric pressure pushes the ground down to the ground. And these spoilers, these aerofoil shaped spoilers, really help to do that. There's an awful lot of manipulation and design going into where the airflow goes on these kinds of cars. Here is an A-level question just showing you and giving you some details, key facts about why this happens and how it's applied to an F1 car. Again, here's another more extensive A-level question, which requires you to compare the Bernoulli effect for an F1 car and for a ski jumper. So both examples we've talked about, obviously they're working in opposing directions, but this is nice level of detail to account for why and how it is applied. Now, obviously what we don't want with vehicles and certain objects is loads of drag, this resistant force slowing the object down. And for that reason, again, this sort of aerofoil shape is even better. We get this lovely laminar flow, the air sticking to the boundary layer, or the boundary layer sticking to the object, as opposed to other shaped objects whereby we get turbulent flow behind. And this obviously relates again to the shape of several designs of structure, particularly our cars. So it actually says wings on cars generate 70% of the downward force, which is amazing, and look at the complex design of it. So there's a quick summary slide on the generation of the downward force, downward lift force. So we've accounted for there what lift is, what the Bernoulli principle is. We've looked at lift and the shape of objects, the angle of attack, the angle of it that it's positioned at. We've looked at Bernoulli's principle, looking at different sorts of examples. What we haven't looked at yet is this Magnus effect and these spinning examples, and that will be the next video.